this video will be the final exam review, and I've been trying to decide on the best way to do this because basically there's not enough time to go over everything. And so what I ended up doing was I asked you guys to email me questions or specific problems to go over, and so I based the final exam review basically on that, and so I went through this competencies and problem types that was posted to the class webpage, and so I took stuff off that, and I'm going to go through that actually, and then when I get to the topic that someone asked me to specifically go over, or the specific problem that I was asked to go over, I'm planning on pointing out that problem in here and then going over it. So anyway, I'd like to get started. So the first thing on this is conversion and mole balances. And he has chapter 2. I actually looked at both chapter 1 and chapter 2 for this. So chapter 1 is where the mole balances were originally derived with the molar flow rates, and then in chapter 2 the mole balances were derived in terms of conversion. So what I recommend doing as far as this is looking at the summary of the mole balances in chapter 1, so basically just look at the summary, and then also look at the summary in chapter 2 of the mole balances. And when I originally took this class, I actually made a chart with both side by side because I felt like it was less confusing to see all the equations together instead of spread out all over the place. So anyway, he has definition, so conversion and mole balances, definition, conversion in terms of concentration, conversion in terms of molar flow rates for flow reactors. So this is where you have the C is equal to F over V naught, or C is equal to Ca naught 1 minus X, so all of those equations. And so for problem types, he has given conversion, find the molar concentration or rates. So if you know what the conversion is, calculate what the concentration or rate is, and then given molar flow rates of reactant and products, find conversion. So basically the opposite, you know what the flow rate is, and so then you find the conversion. And this should all be pretty basic as far as the stuff we have been doing. You pretty much have to do this stuff to solve a lot of the problems we've already been doing. So if you're getting hung up on any of this stuff, definitely go back and review that. And so the next thing is stoichiometry in chapter 3. And so I just wrote down some notes for that. So that's basically the stoichiometric tables, and then there was the tables for a batch system, a flow system, and then a system if you have a variable volume. And I have figure 3-6, which is expressing concentration as a function of conversion. So I'm going to look that up real quick. So yeah, figure 3-6 is this table, and it's literally called expressing concentration as a function of conversion. And I felt like this table was really helpful for looking at a reaction. So it has your reaction, and then it shows, and then it's just a flow chart. So it has, okay, is it liquid or gas? And then if it's liquid, is it flow or batch? And gas, same thing, is it batch or flow? And then it just goes through the various equations you would need in order to solve those problems and get your concentration. And so I recommend looking at that table. And so that's pretty much chapter 3. So he has balancing equations, relative rates for different species. So that's if you know the rate for, so say you have A plus B to C plus D, if you know the rate for A, you should be able to calculate the rate for B, C, and D. And assuming you know the stoichiometric coefficients, which if you have the reaction formula, you should know those. So, and then finding molar rates of all reactants and products given conversion of one of the reactants, usually the limiting reactant. And then he says be particularly careful when the feed is not stoichiometric and there are products in the feed streams. So this is basically going through the stoichiometric, or going through the, what are they calling that? The stoichiometric tables. And so if you're struggling at all with writing rate laws or with the stoichiometry, so as we go through and solve the problems, there's always the stoichiometry step where you write down either the molar flow rate or the concentration or whatever you need. If you're struggling at all with writing those, I recommend reviewing this, and I made some pretty detailed videos on the stoichiometry, so you could also go look at those. And so also in chapter 3 he has reaction rates and rate constants. So the definition of the rate, and so the most common is the moles per liter second, but there's also the catalytic, which is moles per gram of catalyst per second. And then there's different, if you remember, there's different reaction orders. So there's elementary reactions, which that basically means that the coefficients for your reaction follow the stoichiometric coefficients. And so 0, first order, second order, nth order. And then the units of the rate constants depend on the order and type of reaction. But I would recommend knowing how to figure out what the units are based on the actual equation. So you have the rate equation, you know what the units of the rate are, so then you figure out what the units of your constant are based on what units you need. And so don't just try and memorize the units of the rate constant based on the order and type of reaction, because if you get a problem on the exam that asks about units, it's not going to be first or second order. It's going to be some weird order that you have to figure out. So reaction rate constant dependence on temperature, Arrhenius expression. So remember that the reaction rate constant is highly dependent on temperature. And so then given rate at one temperature, find the rate at another by using activation energy. That should be pretty straightforward. Activation energy to double reaction rate if temperature increases by 10%, say. So anyway, just basically a summary for this is just make sure that you understand how to derive reaction rates based on looking at your reaction, and that you know how to calculate the rate constant if you have, so if you have the rate constant at one temperature, make sure you know how to calculate it at another temperature. And I made quite a few, I think I made like 3 or 4 videos on reaction rates. So I know that this and the previous topic, the stoichiometry, are pretty basic, but if you're getting hung up on these problems, it's probably because there's something missing with understanding this basic stuff, because all of these problems are basically just taking this stuff that we learned in chapter 1, 2, and 3 and applying it and combining it all and applying it to whatever your problem is. And so if you know how to do all these things, the problem that you get might still be, you might still have to think about how to set it up, but once you figure out how to set it up, it should just be this over and over and over. So you're just doing the mole balance and the rate law and the stoichiometry. So if you're really comfortable with that stuff, you're probably going to do just fine. But if you're struggling with any of that, definitely review it. And so then the next topic is mole balances and integrated rate expressions. So this was with no volume change, and this was in chapter 4. And so chapter 4 was where it kind of started combining all of this stuff. And what I liked about chapter 4 is it says, one of the primary goals of this chapter is to solve chemical reaction engineering problems by using logic rather than memorizing which equation applies where. And so that's why going through these problems in these logical steps makes them a lot easier than if you just try and memorize the solutions for all the different problems, because there's pretty much an infinite number of possible problems. And so the two tables that I recommend looking at in chapter 4 are, first of all, figure 4-1, and that's this one. And I know that you can't really see that, but I just want to show you which table it is so you can go look it up in your book, because I recommend looking at that. So that's the isothermal reaction design algorithm for conversion. So it just starts out in the general mole balance, and then apply the mole balance to your specific reactor design equation. And so where you're actually going to start is the mole balance. You're probably not going to write a general mole balance each time. And then for 3, is the rate given? If it is, then you just go on and solve your problem, either numerically or analytically. Or if it's not given, then you need to determine the rate law in terms of concentration of the reacting species, and then you go through the stoichiometry. And this has liquid phase or constant volume batch and gas phase. And then for your gas phase, do you have a pressure drop? If yes, you need to add that. For semi-batch reactors, you have this volume that's changing. And, well, and this tells you what chapter each of these things is in. So then you just combine everything, and depending on what your equations are, you might not be able to get an analytic solution, so then you would solve it numerically. And if you get a problem on the exam that you can't get an analytic solution, it's probably going to ask you for the equations that you would put into a solver. So if it's not saying that specifically, then you probably need to solve it. You probably need to get an analytic solution. If you're unsure, then definitely ask. So then or if you're unsure of what's expected in the problem, definitely ask. So the next figure I recommend looking at in this chapter is figure 4-2, and that's called algorithm for isothermal reactors. And so this just goes through again. It has the mole balances for the PFR, CSTR, and batch, rate laws, stoichiometry, liquid or ideal gas, and then it just goes through all of these and kind of shows how you go through and solve that in a orderly fashion. So anyway, he has the mole balances and integrated rate expressions, no volume change, and then mole balance for ideal reactors with no volume change, so batch reactor, CSTR, PFR, and PBR. And then he has space-time, residence time definition. So remember, that's tau, which was V over V naught. And let's see, so then combining mole balances, reaction rate, and stoichiometry to arrive at an algebraic equation or differential equation. So that's what I was just talking about, where this chapter, if you're feeling really comfortable with writing the rate laws and writing the writing the mole balances, writing the reaction rates, writing down the stoichiometry, all this chapter is doing is combining all of those steps to solve your problems. And so this chapter should actually be pretty straightforward, assuming you're feeling pretty comfortable with this other stuff. And then so then he has, if it is one equation, system conversion as dependent variables best. And, well, basically if you have multiple reactions, then you want to use molar flow rates instead of conversion, because you need to write an equation, you need to write a mole balance for each reactant. But if you just have one equation, then you would write it in terms of conversion, and it'll probably be pretty apparent what you need to use, because it'll either give you information about conversion or ask you what the conversion is, or you'll need to calculate it for some other part of the problem. And so I think it'll probably be pretty apparent if you need to solve your problem in terms of conversion or molar flow rate. So with PFR and batch ODE results, and then with the CSTR you get an algebraic equation. So be familiar with integrated rate expressions for 0, first order, second order, nth order. First order reversible reactions for the 3 reactor types. He says you don't need to memorize that. The integrated rate expressions will be provided. Although, with that said, you should definitely know how to calculate those on your own. And then, so problem, given required conversion, find time for batch reactor, or space-time for CSTR. Rate constants will need to be specified to solve these problems. Feed in these cases may or may not be stoichiometric. So this is just where you would go through and set up your problem. So if you have a batch reactor, you would be solving for time, and if for the time to reach whatever conversion you were given. And for a CSTR, you would calculate the space-time, which is that V over V naught. And then invert the above problems. So given the configuration, find conversion. So given the time in the batch reactor, find what the conversion is. So those problems, you should be able to work through both of these problems without too much trouble. So equilibrium considerations, and equilibrium was covered in several different chapters. And so the equilibrium conversion is basically, if you have a reversible reaction, the equilibrium conversion is the highest possible conversion you can achieve. And so you need to know how to write the rate equations for equilibrium conversion in terms of the forward rate constant and the equilibrium constant. And if you're, I don't want to spend time going over that, but if you're having trouble with that at all, then I made a video on that, or I believe it's in chapter 3. So definitely review that. Like, make sure you know how to write rate laws for reversible reactions. Setting the rate to 0. Oh, so then to find the equilibrium conversion as a function of the equilibrium constant, you just set the rate to 0, because when you've reached equilibrium, the rate will be 0. And then make sure you're familiar with equilibrium conversion for first order and second order reversible reactions, and equilibrium constant as a function of temperature, exponential expression that relates the equilibrium constant and the heat of reaction. So make sure if you have the equilibrium constant at one temperature, make sure you know how to calculate it at another temperature, and you would use the heat of reaction to calculate that. So then the next topic was multiple reactors, and that's in chapter 2 and 4. And this is if you have more than one reactor. So it says knowledge about staging reactors, how it affects conversion, performing both graphical, which is the Lebensspiel plot, and equation-based calculations. And so I did an example problem with the Lebensspiel plots, and so I just want to go over that real quick. So this is multiple reactors, and Lebensspiel plots. So let's say you have this plot, and this is FA naught over minus RA plotted with X. And so just say that 60, I mean these numbers don't matter. I'm just want to kind of show an idea of how this works. And so 0.2, say that's 1, 0.8. So let's just say this looks like this. So then the problem is you have, let's say that you have a fluidized CSTR and PBr with equal weights of catalyst. How should they be arranged for the reaction? And then it says in each case use the smallest amount of catalyst weight and still achieve 80% conversion. So you have a CSTR, so CSTR plus PBr, and this is a fluidized CSTR, so it has catalyst in it. So you have, and it says arrange them in a way that you need the smallest amount of catalyst for 80% conversion. So here's 80%. So just looking at this, we know that if you remember the area of the square, so like let's say you have a CSTR that's at 60%. So then this area is the size of the reactor, or in this case the catalyst weight. And then the area under the curve is the volume or the catalyst weight required for either a in this case a PBr or a PFR. So to get the smallest amount for 80%, this is actually what you would want, because your CSTR is, you want to come up with the smallest possible area on this. So this would be the CSTR. And if you change the order of these, so say you put the PBr here, then it would be this entire area for that, and then the CSTR would just be here. So okay, so this is the combination. So this is the CSTR, and this one's the PBr. So then what does the CSTR look like to achieve 80%? So then that would just be this area. And then it says CSTR to achieve 40%. So, I mean, that's the same thing. It's just, you just go up to this curve and it's just this area. So CSTR is just the area. So you just pick off what your conversion is. So say your conversion's out here, go up to the curve and then over. And so then the PBr weight to achieve 80%. So that would be this entire area, because it would be the entire area under the curve. And then the PBr weight to achieve 40%, that's the same thing, just this area under the curve, so this. And so that, I mean, this is pretty, if you're having trouble understanding this, go back and review Lebensspiel plots, and I also did a pretty detailed video on this, so this should be pretty straightforward. The thing that you want to make sure is when you, because this could be plotted with something slightly different, so just make sure that what you're plotting is, so if you multiply this by this, that would, or at least for a CSTR, that would be the volume. But if this was something slightly different, like say that's 1 over minus RA that they're plotting instead of FA naught over minus RA, then you would need to remember to multiply the volume, or you would need to remember to multiply it by FA naught to actually get the volume. So just pay attention to what's being plotted. But other than that, it should be pretty straightforward. The volume of or in this case the weight of the catalyst for the PBr is the area under the curve, and for the CSTR it's just this area of wherever you are on the plot. So from here, so this would probably be like 90% right here. So you go up to the curve, go over, and then it's just whatever's here. So say that's 18, so 18 times 0.9. And then I also wanted to do a problem. So this is graphically, I wanted to do a problem mathematically too. So I'm going to erase this. So this is reactors in series. So let's say that you have a liquid phase reaction. A plus B to C. It's elementary, isothermal. It's a flow system. So Ca naught is equal to Cb naught is equal to 2 moles per dm cubed. And the volumetric flow rate for each stream, so you have, I'll just write the volumetric flow rate of each stream is equal to 5 dm cubed per minute. T naught is equal to 300 K, and the streams mix immediately upon entering the reactor. So you have 2 reactors available, so 2 reactors. You have a 200 dm cubed PFR, and you have 800 dm cubed, actually, sorry, this was the CSTR, PFR. And K is equal to 0.07 dm cubed per mole minute. This is at 300 K. E is equal to 20 kilocal per mole. So what conversion would be obtained if the CSTR and PFR were operated at 300 K and connected in series? And then also in parallel with 5 moles per minute of each. So anyway, so for the first one you have, so let's say this is a CSTR, this is the PFR. So let's say you have X naught coming in, which is 0, and then you have X1 coming out of the CSTR and X2 coming out of the PFR. So I'm going to erase some stuff real quick. The first thing you want to do is a mole balance on the CSTR. So mole balance CSTR. And we want to write this in terms of conversion because that's what we're working with and looking for. So V is equal to FA naught X out minus X in over minus RA. This is out. So if you go back and look at the mole balances at the end of chapter 2, you'll notice that they're actually written in terms of X in and X out. And so when you're solving these problems that have multiple reactors, you're still doing the same thing. You're just having to solve the problem more than once because you have the CSTR, and then when the stream goes into the PFR, some conversion has already occurred. So you need to calculate what the conversion coming out of the CSTR is, and then that's what's going into the PFR. So the problem is still basically the same. So we'll just solve this twice. So we'll solve it once for the CSTR and once for the PFR. So now the rate law, so minus, and I said it was elementary, so this is just K, Ca, Cb. Stoichiometry, I said it was liquid, so this is Ca naught 1 minus x, and Cb is equal to Ca naught 1 minus x. So then you just combine everything. Since this is a CSTR, you're going to get an algebraic expression. And also, in this case, the xn is 0 because that's the CSTR's first. So V is equal to Ca naught V naught multiplied by x. And I'm just going to change the x out to x1 because that's how I've labeled it over there. And this is over K Ca naught squared 1 minus x squared. So then that cancels. And then this is just plug and chug. We know what V is. It's 200. We know what V naught is because it's the two streams added together. So it was, I believe it's 5 plus 5, so it's 10. And we know K because it was given at 300 K, which is the temperature we were told the reaction is at. And Ca naught was given, it's 2. And we're solving for x. So if we plug everything in, and this is also x1. So if we plug everything in and solve for x, we get the x1 is equal to 0.55. So now I'm going to erase some stuff and do the PFR mole balance. PFR mole balance. And so V is equal to Fa naught x1 to x2 dx over minus Ra. And so this is what I'm talking about. Like the equation on that table is from x1 to x2. But if you just have one reactor, this would just be 0 to x. But in this case, we have some conversion coming in from the CSTR. So this x1 is what we just calculated. So, and I'm not going to go through all the details of the math of this because this video is going to be way too long. So I'm just going to write what I got when I integrated that. So I plugged in the rate law and the stoichiometry are still the same. So you just plug that in and you get that V is equal to V naught over K Ca naught 1 over 1 minus x2 minus 1 over 1 minus x1. And this integration is on that table in the appendix. So then if you plug everything in, we know what the volume of the PFR is. We know V naught, K, Ca naught, and we know x1. So x2 is equal to 0.93. So let's say that they're connected in parallel now. So we have the CSTR. And we have a PFR. So this is solved exactly the same way. You would calculate the conversion for the CSTR and the conversion for the PFR. The only difference is you're using half the flow rate because this time they're not combined going in. So the flow rate, instead of 10, what was it? Instead of 10 dm cubed per minute, it would be 5 dm cubed per minute. And so you would go through and calculate x for both of these using that different flow rate. And then the overall conversion is just the average. So x is equal to x CSTR plus x PFR over 2. Anyway, then this just has equation for CSTR in series, and I think I kind of went over that. So equation for incremental conversion of CSTR and PFR as we go from conversion 1 to conversion 2. And then it just has given rate parameters and reactor configurations, so volume and flow rates, etc. Find conversion in any combination of multiple reactor scenarios. And So that should be pretty straightforward. I mean, it might take some time because you need to go through and do the calculation for each reactor, but it should be pretty straightforward. And then, so one outcome is given in a reactor, say conversion for a given volume. Now you are asked to figure out what would happen if an additional reactor is placed either before or after the given reactor. And then it says, example is the last problem in midterm 1. So I'd recommend going and looking at that. So then chapter 4, volume change in reactors. So the volume change is only important if you have a gas phase reaction. And you need an equation of state. So we've been assuming ideal gas law. Know how to calculate epsilon. Expressions for concentrations in terms of epsilon, conversion, pressure, and temperature. So that's you should, if you understand the stoichiometry for the gas phase stuff, you should know that. Writing mole balances with volume change, and so we've gone over that. That's in chapter 3. Combining mole balances, rate expressions, stoichiometry to obtain one equation. So that's basically you've gone through, written down all your equations for your. So you've gone through the mole balance, stoichiometry, or mole balance, rate loss, stoichiometry. Now combine it. So given required conversion, find time for batch reactor or space time for CSTR. And then invert the above problem. So given reactor configurations, find conversion. So as long as you go through these problems, I mean, so these are the gas phase or the volume change. It's the same process, you're just writing your stoichiometry different to account for the change in volume. So anyway, the next topic is different types of reactors, and he specifically mentioned semi-batch and writing mole balances for a so know how to write mole balances for a semi-batch reactor. And using either conversion formulation or number of moles formulations. Example, and it says just look at the example problems in the text and the homework that you worked on. And so very few problems can be solved analytically. So he recommends looking at the semi-batch examples from midterm 2 because, let's see. Yeah, and then for most semi-batch reactors, you need to use an ODE solver like Polymath or MATLAB because you're going to end up with a bunch of coupled ODEs. So I was going to go through an example for a semi-batch. So semi-batch. So let's say you have A plus B to C plus D plus E. You have 1.5 molar solution of A fed at a rate of 0.1 mole per minute to 1500 dm cube of 0.75 molar solution of B. It's elementary, isothermal. K is equal to 5.1 dm cube per mole hour. The volume, well, so the reactor can hold 2500 dm cube. And then this problem says show the equations you would solve in Polymath or MATLAB. So this is a case where you're not going to be able to get an analytic solution for this, so you just need to write down the equations you would solve. So I'm going to, because of time, so normally with these problems I would write down the mole balance and the rate law, and then rewrite the equations I would actually enter. But I'm just going to write down the equations that I would enter just for time. So equations entered. So first of all, we're adding A. And so the mole balance for A is dCA dt is equal to Ra plus V naught over V Ca naught minus Ca. And then for B, so we need to write a mole balance for each reactant. So dCb dt is equal to Ra minus V naught over V Cb, and dCc dt is equal to minus Ra. And these would, actually I'm going to take a step back. I mean, so this is actually Rb and Rc minus V naught over V C sub C. And so, and dCc dt is equal to dCd dt is equal to dCe dt, so I'm not going to rewrite those. And so you can get these rate laws. We know what Ra is. We know that Ra is equal to minus K Ca Cb. And I wrote it like this instead of, because normally you write it as minus Ra is equal to K Ca Cb, but I just wrote Ra is equal to minus K Ca Cb because I'm writing down the equations how I would enter them into a solver program, and you can't enter the rate of disappearance. You have to put it in as the rate of appearance. So that's why I wrote this like that. So then Rb is equal to minus Ra. No, sorry. These are the same because you have A plus B. So Rb is equal to Ra. So that's why when I wrote this, I had Ra here, and then Rc is equal to minus Ra. So then this would be minus Ra. And this is exactly how I would enter it. So although I wouldn't include these two equations, I would just have this, because I wrote these all in terms of Ra. So then you would just, if you have a problem like this on the exam where it's saying what would you put in your solver, make sure you write down all the constants too, just so that we know that you know what you're putting in. So in this case, Ca naught is equal to 1.5 because you're feeding 1.5 molar solution of A. K is equal to 5.1. That was given. V naught is equal to 1500 because that's what you have initially. And then your volumetric flow rate is equal to Fa naught over Ca naught. And then the big equation you need for a semi-batch is that V is equal to V naught plus your volumetric flow rate multiplied by time. Make sure you write this down because, and if you're actually solving your equation, make sure that you use this equation because this V is changing, and so you need to take into account the change in the volume. So the next one, he has different types of reactors. So recycle reactors, and recycle reactors aren't in the book. So there's the notes and what's on the author's web page. I also made a video on recycle reactors, so you could look at that. So just the basic definitions, integrated forms of equations with and without volume change. And then example problems are given operating aspects of the reactor, find conversion. And given with conversion specified, find the recycle ratio needed. So I'm going to go through a recycle reactor problem. And I believe this problem was on one of the finals he gave you to, or one of the previous year finals. Someone asked me to go over it, so. Recycle reactor. So this is a first order. A to B. Ca naught is equal to 4 moles per liter. V is equal to 200 liters. V naught is equal to 20 liters. R, which is the recycle ratio, is equal to 5. X is equal to 0.6. So it says, well, okay, so you have the recycle reactor, and it says you want to replace it with a CSTR PFR combo. What volume of the PFR is required to get the same conversion as the recycle reactor? And so the reason why the information you need to get from the recycle reactor is you weren't given your reaction rate constant. So we need to calculate that from what we know about the recycle reactor. So I'm going to go through the derivation of the integrated mole balance, because in the problem in the solutions he gave you for this problem, he started with the integrated form of the equation, so basically an integrated form of a first order recycle reactor mole balance, but on one of your exams you had to go through this derivation, and so even if you don't end up having to do it, I think that it's something you should know how to do. So starting with the recycle reactor mole balance, we have, so let's write mole balance. We have V is equal to FA naught 1 plus R over R plus 1 X naught D XA over minus RA. And we derived this equation on one of the homework assignments. I can't remember which one, but I would recommend maybe going back and reviewing that. And so anyway, the rate law is minus RA is equal to KCA, and we know that because it's first order. Stoichiometry, I'm assuming it's liquid, so Ca is equal to Ca naught 1 minus XA. And so then we need to combine everything. So I'm going to erase some stuff real quick. So combining this, we get that V is equal to Ca naught V naught, because this is FA naught, right? So FA naught, and this is 1 plus R over R plus 1 X naught to X naught. So D XA over K Ca naught 1 minus XA. And we can cancel this out. And I'm going to also pull the K out. And so then, I'm going to pull the K out, and I'm going to divide by the volumetric flow rate over and multiply K over. So then I have V over V naught, and just remember this is tau. So that's kind of a bad way to write that. That's tau K. And I'm going to also divide over the R plus 1. So then this is equal to R over R plus 1 X naught D XA over 1 minus XA. And so then I'm just going to integrate this. So I get tau, shall I go down here? Tau k over r plus 1 is equal to the natural log 1 over 1 minus x. And then I have the limits of integration here, so x naught over r plus 1 x naught. So I'm just going to erase some stuff real quick. So then, applying those limits, and this is just algebra at this point, but I wanted to go through it because I felt like there was just a lot of confusion with this. So tau k over r plus 1 is equal to the natural log 1 over 1 minus x naught minus the natural log 1 over 1 minus r over r plus 1 x naught. So the next thing I want to do, I just want to combine these natural logs. So tau k over r plus 1, and this is equal to 1 over 1 minus x naught divided by 1 over 1 minus r over r plus 1 x naught. So then this is equal to the natural log x naught r minus 1 x naught minus 1 r plus 1. And so then just pulling the r out so this looks a little better, tau k over r plus 1 is equal to the natural log r x naught minus 1 over x naught minus 1 over r plus 1. So I think that you could actually use this equation to solve for k, but I want to take this a step further and show you how you get this in the form that you usually see as the integrated rate expression for first order recycle reactor, because it's really just one more step. And on the, like I said, on the on the solution for that practice final, he just started with this equation that I'm about to finish deriving. But all I was saying is if you went through and calculated this, I'm pretty sure you have everything. You could just calculate k now. But just taking this a step further, we know that x naught is equal to Ca naught minus CAF over Ca naught. And so then we can just plug this in for x naught. And if we do that, we get, and I'm not going to go through the details of the algebra of that too, but if you plug this in for x naught and simplify, you get that tau k over r plus 1 is equal to the natural log of Ca naught plus r CAF over r plus 1 multiplied by CAF. And so then we can calculate k. We know what Ca naught is. CAF is equal to Ca naught 1 minus x, which is happens to be 1.6 if you go back and I can't remember what Ca naught was, but it was 4. So 4 multiplied by 1 minus 0.6. And so then you can plug in everything else. We were given r. We know tau because we know v and we know v naught. We just calculated CAF and we know Ca naught. So going through that, if you plug everything in, you get that K is equal to 0.1339. So like I said in this exam solution, he started with this equation. And you'll probably have this equation on your formula sheet, but I just wanted to show the derivation because I think a lot of people were caught off guard when they had to actually go through this derivation on, I think it was the second exam. So if you're not sure, I mean, it's still the same thing. You just start with the mole balance for a recycle reactor. Just make sure you're starting with the right equation. And then it's still the same thing. It's just the mole balance, rate law, stoichiometry, combine everything, and solve it. There's a little more algebra, a little more math involved, but it's still the same process. So then he told us that this recycle reactor was replaced with a CSTR-PFR combo. So I'm taking that to mean that you have a CSTR followed by a PFR. So I'm actually thinking I might skip going through this because this is exactly what I just did. And so you would go through the mole balance for a CSTR and plug in the rate law, which you already calculated what the rate law was, stoichiometry, and then you solve for x, and you'll get a value for x, and then that will be your x in for the PFR. So then you go through and you calculate the volume for the PFR. So that, I don't want to go through that because the video is getting kind of long, and that was what I just barely did in a previous problem. So anyway, the main point of this was to show you the recycle reactor stuff anyway. So I went through the recycle reactor. So now he has pressure drop in reactors. That's chapter 4. And just remember with that you're basically doing all the same stuff. You're just adding in the pressure drop so you're changing your rate law to account for the pressure drop. And then you need to write an equation for the pressure drop. And remember that in order to get an analytic solution, you basically need to assume that there's no volume change. So basically you need to say that epsilon is equal to 0. If you don't do that, then you'll end up with 2 ODEs, and you need to use a solver to solve those. You can't really get an analytic solution. And so I'm not planning on going over a problem on that because nobody really asked, and it's kind of the same thing as the other stuff. You're just taking one more step. All you're doing is adding in the pressure drop. And so anyway, for the data analysis, I wanted to point out table 5-1. And I went over this table in pretty good detail on a video, so that might be a good way to review it, or you could just look at the table. So table 5-1 is steps in analyzing rate data. And so this goes through how you would do this. So and remember there are a couple different ways you can do it. So first of all, you would postulate some kind of model. So most of the problems we've been doing are using the power law model. And so then you select your reactor type and corresponding mole balance. So like in the example, so they're using a batch reactor. And then you process your data in terms of a measured variable. And so, you're going to be given data. And so then you take you take your mole balance and you put it in a form that you can plot a straight line. And so so for this one, you take the natural log of it. And So then you end up with the natural log of dCA dt, and so you're probably not going to have dCA dt. You're probably going to have, if you're measuring data, you're probably going to have the concentration. And so you would need to calculate dCA dt, because you'll probably have concentration and time. And so there were 3 different ways you could do that. You could use the graphical method, the finite differential method, or the polynomial method. And so then you plot the natural log of dCA dt versus the natural log of Ca, and then you can find the reaction order, and so the reaction order was the slope, and you could find K from the y-intercept. And then the other method you could use was the integral method. And this method was good if you knew what your reaction order was. If you don't know, then you had to guess it and then go through and do some plotting to figure out if your guess was correct or not. And if it wasn't, then you had to guess another order and try again. And the other method you could use was nonlinear regression, but I doubt you're going to be doing that on the exam. So I wanted to go through an example problem of data analysis. This is just one example out of, there are a million different problems I could have done on this, but I mean, if you definitely want to be familiar with this, so if you're, I would go back and review it, and I'm not sure if you're allowed to note sheet, but if you are, on the note sheet I had when I took this class, I basically just wrote down the steps for depending on what you have. So, and because this is another one of those problems where if you go through the steps, then it's going to be pretty straightforward, but if you just try and jump around, it's probably going to be really confusing. So anyway, so you have a liquid phase. It's irreversible. A to B in a CSTR. So this is a little bit different because you have a CSTR instead of a batch reactor, so just keep that in mind. So, and then tau is varied as, so they vary tau and then they measure concentration, and Ca naught is equal to 7.5 moles per liter. So they did several runs, so 1, 2, 3, and 4. And they varied tau and measured Ca. So when tau was 1, Ca was 3.2. When tau was 15, Ca was 0.72. When tau was 30, Ca was 0.46. And when tau was 100, Ca was 0.21. And then it says determine the reaction order and the rate constant. So the first thing you want to do is CSTR mole balance. And this will still be following the same steps on this table because they did a mole balance for, if you look at this, they select their reactor type, this is step 2, and then the corresponding mole balance. So we have a CSTR, so V is equal to Fa naught minus Fa over minus Ra. And this is the mole balance that's at the end of chapter 1. And then we want this in terms of concentration because that's what we have here. So I'm just going to say, well, we want it in terms of concentration and tau. So Ca naught minus Ca multiplied by V naught over minus Ra. And then we can divide this V naught over, so then we get tau is equal to Ca naught minus Ca over the rate. And then for the rate law, and this is slightly out of order because the first step was to postulate a rate law. So that's what we're doing now. And so we're saying that minus Ra is equal to K Ca alpha. And so what we're looking for is K and alpha. So then we can plug this in. So plugging that into there. So we get that tau is equal to Ca naught minus Ca over K Ca alpha. And then we want to rearrange this so that we have the K Ca alpha on one side. So I'm going to erase some stuff real quick. Because basically we want to take the natural log of this and have some form of the equation that will get a straight line. And so we can just multiply that over and divide the tau over. So then we have Ca naught minus Ca over tau is equal to K Ca alpha. So then you can take the natural log of this, and so you get the natural log of Ca naught minus Ca over tau is equal to the natural log of K plus alpha, the natural log of Ca. So then this is y is equal to b plus mx. So alpha is the slope, natural log of k is the y-intercept. So now what you want to do is plot this. So you're plotting, so plot the natural log of Ca naught minus Ca over tau versus the natural log of Ca. So what I did when I solved this problem was I said, okay, so we have the data from the runs. So we had 1, 2, 3, 4. And I just calculated the natural log Ca naught minus Ca over tau, because you have everything you need to calculate that. So I got 1.46 minus 0.79, etc. And then I also calculated the natural log of Ca. So, and then the way I solve this problem, it specifically says in the problem to plot this. So if you have a problem that says to plot it, that's what you need to do. But I just did linear regression and got a solution for this. And so I got that y is equal to 1.5x minus 0.286. So then comparing it to this, alpha is equal to 1.5, so that's the order. And k, so this number is equal to the natural log of k. So then you can solve for k, and I got that k was equal to 0.75. So make sure you know how to do linear regression and plotting on your calculator, because that's gonna, if you get a problem like this, that's gonna make solving it a lot faster. The next topic is multiple reactions, and so I wanted to point out table 6-1. So this is table 6-1, and it's mole balances for multiple reactions. So this just has the mole balances for batch, PFR, CSTR, and semi-batch when you have multiple reactions. And then if you look at the next page, at figure 6-5, you have the algorithm for the isothermal reaction design for multiple reactions. And that might be worth looking at too. So it goes through there, you have your reactions, so you number each reaction. You have the mole balance and your net rate laws. Definitely make sure you know how to write net rate laws. Stoichiometry, pressure drop, and then combining. And likely for these problems, you'll need an ODE solver. And so I had an example problem on this. All right, so this is for a series reaction. This is a problem that someone asked me to go over. So you have A to B to C. This one's first order, and this one's second order. It's a CSTR. And it says determine concentration of intermediate product B if tau is equal to 5 minutes. And then it gives you K1 is equal to 0.2 and K2 is equal to 4. This is liters, mole, minute, and this one's minute minus 1. Ca naught is equal to 1 mole per liter. So the first thing you want to do for this is a mole balance on the first one. So mole balance. And so this is a CSTR, so you just have V. I'm going to skip straight to the equation I had before, which was tau is equal to Ca naught minus Ca over minus Ra. The rate law is first order, so it's K1 Ca. So then you just combine this, and you have tau is equal to Ca naught minus Ca over K1 Ca. And so then you can calculate Ca. So I'm going to solve this for Ca. So Ca is equal to Ca naught over K tau plus 1. And I'm just going to leave that like that for now and do a mole balance on B. And you'll, in just a second, you'll see why we need to calculate Ca. Right. Mole balance on B. So same thing as a CSTR, so tau is equal to Cb naught minus Cb over minus Ra. And this is where the rate law is different. So you have a series reaction, so you have A to B to C. So you need to get a net rate law for B, because what you actually have, if you number these reactions, you have A to B, and then you have B to C. And so the rate law would be equal to the rate of the first one plus the rate of the second one. And so this is equal to the, so let's just say we already know the rate of A, and B is the, so minus Ra is equal to Rb. So that means that this is equal to K1 Ca plus, and then the Rb2 is equal to K2 Cb, and that's squared because it said it was second order. So this is plus K2 Cb squared. So make sure you know how to write these net rate laws. trying to remember what chapter that's in. I think that's in chapter 6. Plus I did a video on this, so definitely review that if you're confused about how to get this. So then you just combine this and solve for CB. So combine, and then tau is equal to CB naught minus CB over K1 CA minus K2 CB squared. And I didn't actually physically solve this for CB. I just plugged everything in and solved for CB on my calculator. But you know what everything is, so you know CA because you can calculate it here, because we know everything we need to calculate CA. And I can't remember what it was, but you just calculate CA, plug it in here. We know K1 and K2. We know CB naught, and we know tau. So anyway, for CB, you end up getting 0.135 moles per liter. So the next topic is heat effects. And so I'll just read through. Actually, I wanted to point out table 8-1 for this. So let's see. So there's actually some pretty useful tables in chapter 8. So definitely review that for the heat stuff. So table 8-1, energy balances of common reactors. And so this has the energy balance for adiabatic reactors, a CSTR with heat exchange, PFR, PBR with heat exchange, and then all of these in terms of conversion, molar flow rates, semi-batch, and multiple reactions. And just be sure that if you pull an equation off this table that you can. So for instance, this for the adiabatic, this is assuming that your work is 0 and that delta C sub P is 0. So if those aren't the case, then you need to use an equation that accounts for those. And so just make sure that you're using an equation that applies to your situation. And so one thing he said to look at was, or the topics are, so exothermic, for an exothermic reaction, the equilibrium conversion decreases with temperature. For an endothermic reaction, the equilibrium conversion increases with temperature. And then he said, if you have interstage cooling or heating, then, well, I just wanted to draw what that looks like. So let's say, I'm going to get a different marker. So let's say you have, so this is X and T, and this is an exothermic reaction, so Xe is decreasing with temperature. This is Xe. That's your equilibrium conversion. And so then you have your, so this is this curve, you derive this from your mole balance equations. And so then you also have the curve that you derive from the energy balance. It's not a curve, it's a line. So for this reaction, your energy balance would look like this. So then your conversion is wherever these meet. And so you can get a higher conversion, in this case, if you have interstage cooling. So let's say this goes up to here, and then you cool it down, and then it will go up again, and then you cool it down, and then it goes up, and let's say it crosses there. So that's how you would get a higher conversion. And so this is for exothermic. So then the case of an endothermic reaction, you would have interstage heating, and so your conversion curve looks like this. This is Xe. And and I'm just going to write, this is X mole balance. So for this one, it would come up like this. So this is X mole balance. And then let's say you heat it up. And then you heat it up again. And then it goes up. And then you heat it up again. And then it crosses up here somewhere. So that's how that would work for the interstage heating and cooling. And so just make sure you're aware what happens to the equilibrium conversion depending on if your reaction is exothermic or endothermic. And then he has a CSTR, adiabatic or with jacket equations, calculation of multiple steady states, and PFR, finding temperature and conversion with volume of the reactor. And for those, you'll usually need an ODE solver because you're going to end up with, well, for the CSTR, it's probably algebraic, but for the PFR, you're going to end up with two coupled ODEs. So I have a couple example problems. Effects. So this is elementary. Second order adiabatic, and it's a CSTR. So it's A plus B to C plus D. CA naught is equal to CB naught is equal to 2.4 moles per liter. T naught is equal to 300 K. V naught is equal to 15 liters per minute. And then CPA is equal to 20. CPB is equal to 15. CPC is equal to 15. And CPD is equal to 20. So, okay, and then also the heat of reaction is equal to minus 7,000 at 300 K. K at 300 K is equal to 0.00045. E is equal to 12,000. So looking at this real quick, delta C sub P, which is C sub PD minus C sub PC, C sub PD plus C sub PC minus C sub PB minus C sub PA is 0, so delta C sub P is equal to 0. So that's good to know because that means that we can pull an equation off that table. So we want to know the reactor volume when X is equal to 0.75. So the first thing you want to do is a mole balance. So V is equal to FA naught X over minus RA. Next is the rate law. Minus RA is equal to KCA CB. So it said it's elementary second order. Stoichiometry. CA is equal to CA naught 1 minus X, and CB is also equal to CA naught 1 minus X, because, well, I'm assuming it's liquid. So then we want to do an energy balance. And we can, so we want to, I'm going to use the energy, well, it says it's adiabatic, so I'm using the adiabatic energy balance, which I believe is equation 1 on that table. So T is equal to T naught plus X multiplied by the heat of reaction over the sum of theta I CPI. So I'm going to erase some stuff real quick. We can expand the energy balance. So T is equal to T naught plus X multiplied by the heat of reaction over, and then we have theta A CPA plus theta B CPB. And technically this would also be theta C CPC plus theta D CPD. But then when you start looking at these thetas, first of all, theta A is 1, theta B is 1, but theta C is equal to theta D is equal to 0. So just make sure you don't add these in if they're going to be 0. And let's see, so then we can solve this equation for the temperature. And what you want to do here is solve for the temperature of the reactor, and then you calculate K at that temperature, and then you can solve your, and then once you have K, you can solve your mole balance for the volume. So if we plug everything in here, we get that T is equal to 450 K, and then I'm going to put solve for K at 450, and so K ends up being equal to 0.3694. And so then we can combine the stoichiometry and rate law, and so we get that V is equal to Ca naught V naught X over K Ca naught squared 1 minus X squared. So then the Ca naught cancels, and we know everything else. We know V naught, we know Ca naught, we just calculated K, we know X. So we end up getting 203.05 liter. So I'm going to erase some stuff, and I wanted to do one more heat effects problem. Okay, so this one's elementary, reversible, liquid phase, A to B, and it's reversible, and it's in a CSTR that's jacketed. And I don't think I'm going to write down, well, maybe I should. So first of all, you have pure A that enters, and then K is equal to 1.25, E is equal to 40,000, your equilibrium constant is equal to 75 at 120 degrees C, and this one is at 27 degrees. This one's at 100 degrees C. I'll just write down what you have. So you have UA, TA, CPA is equal to CPB is equal to 45. You know the volume, you know V naught, and you know FA naught. So anyway, then you have, the reason why I'm kind of skipping over that is because the whole point of this problem is to show you how this graphical method works. So I already mentioned this. You can calculate, if you go through your equations, so you write your mole balance, rate law, stoichiometry, and then you go through the mole balance and you solve for X. Then you can get a curve, and so in this case it gives you a curve that looks something like this. So this is your X mole balance, and this is plotted with X versus T. And so the question for this problem is how many steady states are possible, and determine the conversion in temperature at the stable steady states. So what we need to do is calculate X EB. So we need the energy balance. And so we have a CSTR with a heat exchange. And so I'm going to pull the equation straight off this table 8-1. And so this is equation 2, CSTR with heat exchange. And this is assuming that you have a large coolant flow rate. So just keep that in mind. So XEB is equal to, actually write it over here. So x EB is equal to UA over FA naught T minus TA plus the sum of theta I CPI T minus T naught. And this is all over the heat of reaction. And then this will end up just being CPA because theta A is 1 and theta B is 0. So then what you do is you have everything you need to plug into this energy balance equation, and you should be able to plot a straight line. And I kind of drew this poorly. This probably looks more like this. And so when you plot this straight line, you end up getting something that looks like this. And so everywhere that this crosses this line is a potential steady state. So you have three, in this case, you have three possible steady states. And you can figure out what the temperature and conversion is because you just go down here and look at the temperature, go over here, look at the conversion. So that's the conversion for this state and the temperature for that state. Same thing with this, and same thing with this. So if you're given the if you're given the curve for the mole balance, then you just need to plot this energy balance. But if you're given, say you're just given data and you need to create these plots, you would calculate whatever your x mole balance is. And remember, you get that just by going through the mole balance and plugging everything in and solving for x. And then you plot that, and then you do the same thing for the energy balance. And so I'm kind of speeding up a little bit because this video is getting kind of long, but this is all in chapter, let's see, chapter 8. So I would definitely review this graphical method, and I did a video on that, so you can go watch that. And just make sure that you kind of understand how these plots work and what equation you need to use. And I think those are the important points for that chapter. So then in chapter 10 and 12, we did the catalytic reactions. And so, the main point of that is basically that in a catalytic reaction it has three steps. So it has the absorption, surface reaction, and desorption. There's also diffusion, but we didn't, well, we did that, we talked about that a little bit, but in deriving this where he has write the three stages of reaction, so know how to write the equations for those three stages, and then make sure you know how to derive the rate law for whichever one's limiting. So the example problem we did, we assumed that the surface reaction was rate limiting. And so make sure you know how to go through and do the derivation depending on what you're given for the limiting reaction. And so this is really similar to the net rate laws. And so if you're struggling at all with that, you're going to have a hard time with this. So definitely make sure you understand how to write the net rate laws. And so then the next one is the diffusion in the catalyst. And so that's where you have a catalyst, and there is a certain amount of, so the reactions we've been doing so far, we've been assuming that they are ideal. And so, but really it's not ideal. So what you're doing with this, where you calculate this effectiveness factor, is you're saying, okay, it's not ideal, so this is what I actually got, and this is what I would get if it was ideal. And so this effectiveness factor is basically dividing what you got, or what you actually got, divided by what you would get if it was ideal. So you can calculate that and multiply it by your rate law and calculate what you're actually getting. And I wanted to go through an example problem with that. This is an internal diffusion problem. So, let's see, I wrote the order, but I can't see it suddenly. But anyway, so you have A to 3B. It's in a PBR. Your rate constant is 0.8. X is 0.75. FA naught is 4 moles per second, and it's 40% A and 60% inert. T naught is equal to 127 degrees C, and P naught is equal to 5 atmospheres. And your internal effectiveness factor is 0.7193. What weight of catalyst is needed? So the first thing you want to do is a mole balance. And if you're not given this in the problem, you'll need to calculate that. So review how to calculate that, but I wanted to show you how you apply that into the method we've already been using to solve these problems. So your mole balance is FA naught dx dw is equal to minus RA, because you have a PBR. The rate law is minus RA is equal to the effectiveness factor multiplied by K CA. So this is how that applies. You basically multiply your rate law by the effectiveness factor. And the reason why it's multiplied by the rate law is because so the rate law, the way you've been writing it, is basically assuming that it's ideal, but in this case it's not really ideal, and so you're taking that into account. So then the stoichiometry, and this is gas phase, so Ca is equal to Ca naught 1 minus x over 1 plus epsilon x, but I'm assuming no pressure drops, so assume no pressure drop. Somebody erase some stuff. So then you just combine everything. So you should see that the only difference between how you solve this problem and all the other ones is you're just multiplying your rate law by the internal effectiveness factor. And for this problem it was given, but you might need to calculate that. But that's the only difference. So combining this, we get FA naught dx over dw is equal to, and then we just plug the rate law in, so 1 minus x over 1 plus epsilon x. Separate and integrate, so to have 0 to x, 1 plus epsilon x over 1 minus x dx is equal to 0 to w, this effectiveness factor multiplied by K Ca naught over Fa naught dw. So I'm going to erase some stuff real quick. So this integral is on the table in Appendix A, so I just got it off that. So this is 1 plus epsilon natural log 1 over 1 minus x minus epsilon x is equal to effectiveness factor multiplied by K Ca naught over Ca naught V naught W. So Ca naught cancels. And then we need to calculate epsilon. So just looking at this equation, the only things we don't have epsilon, and we don't have v naught, so we need to calculate those. So epsilon is equal to ya naught delta, and ya naught is the mole fraction, and it basically told us that that was 0.4. And then delta is, so the reaction was A to 3b, so delta is 3 over 1 minus 1, so it's 2. So epsilon is 2 times 0.4 is equal to 0.8. And then we can get v naught by applying the gas law. So P v naught is equal to ft naught RT. And so then v naught is equal to ft naught RT over P. And if you plug everything in using the right gas constant, you get 26.24 liters per second. So then you have everything you need to plug into this equation. We know x, epsilon, we know what the effectiveness factor is, we know k, we know v naught. So if you plug everything in and solve for w, you get that w is equal to 86.4 kilogram. The last topic was resonance time distributions, and that's chapter 13. So since we didn't actually do any homework on this, I'm not sure exactly what you'll be expected to know, but he has definitions, the resonance time distribution for ideal reactors, and given the resonance time distribution and the segregated flow model, find conversion. So I wanted to go through a problem with where you're given the resonance time distribution, and then I want to use the segregated flow model to solve for conversion. So I'm going to erase some stuff real quick. I just wanted to also talk about the definitions of this stuff real quick, just because I haven't done a video on this stuff, and I'm not going to before the exam. So first of all, so you have this thing called the resonance time. So just taking a step back, we've been assuming all of our reactors so far are ideal, but in reality they're probably not ideal. For instance, for instance in a CSTR, the ideal CSTR is assuming that the fluid is distributed immediately and it's perfectly mixed, but in reality, it's probably not perfectly mixed. There's probably spots, so let's say you have a CSTR and you have fluid coming in and fluid coming out. There's probably, they call them dead zones, so like maybe here and here, where the fluid is just sitting there. It's not really moving at all. And so basically, it's maybe not perfectly mixed. It's the other thing with ideal reactors is you're assuming that every molecule spends exactly the same amount of time in the reactor, but in reality, they probably spend different amounts of time in the reactor. So some molecules flow through the reactor immediately, and others sit in the reactor for a while and don't exit immediately, like if there are some in these dead zones, and molecules flowing through the middle of this reactor might go straight through. So the E of T is a way to describe what the molecules are doing in the reactor. So this is called the resonance time distribution. And so it describes how much time different fluid elements spend in the reactor. So for instance, if you have, so say it looks like this, say this is time t, this is E of t, So it probably looks something like this. So you have some molecules here that spend almost no time. You have some here that spend a lot of time. And then you have kind of in the middle where you have molecules that are spending this much time. So that's kind of what this is. And this function looks different depending on what reactor you have. And so I don't want to get into all the details of that because I think sort of the point of this is to just sort of explain what that is. So the other thing that he said to know about and that I'm going to do the problem on is the segregated flow model. So the segregated flow model, so going back to this reactor, this is assuming that you have, so let's just say that you have a bunch of, they call it globules in the book, but you have these globules of molecules. And what these are is it's assuming that these molecules don't mix with each other. That's why it's called segregated. And so, and each one of these spends so say these ones are spending 1 minute in the reactor. So every molecule in this batch is in there for 1 minute. And then say this one is 5 minutes. Say there's one over here that's an hour. So basically these don't mix, and it just lumps together the molecules that are spending the same amount of time in the reactor. And so this is for a CSTR. For a PFR, it would correspond to the exit stream. So for a PFR, you have this. So it would be these various streams as they exit. And so then what you can do with this model is you have the mean conversion of globules. I'm just going to call it that because that's what they use in the book. Spending between T and T plus delta T in the reactor. So it's the mean conversion. And so this is the globules between at this time and this time. This is what the conversion is of them in the reactor. So, and then this is equal to conversion achieved in globule after time t in reactor. So this is equal to x of t. And then this is multiplied by the fraction of globules that spend between T and T plus dt in the reactor. So in other words, this is multiplied by E of T dt. So we have dx dt is equal to x of t E of t. And so what we want to do is sum over all of the globules in order to, so the way you do that, coming back over here, so x mean is equal to, and then we want to go from 0 to infinity, xt multiplied by E of t dt. So then the way you can solve this problem is another way to look at these globules is you can assume that they are all batch reactors. So each one of these is an individual batch reactor because nothing is entering or leaving it. And so you can solve x of t for a batch reactor, and then you multiply that by this resonance time distribution function and integrate it over your time. And so hopefully that's a little more clear when I do this example problem. This is kind of abstract. So I'm going to actually erase all of this. So yeah, this is kind of abstract, and I'm kind of going through it fast because it's the end of this review. And I'm not really, yeah, so anyway. So I want to do an example problem. So this is so you have a resonance time distribution function. And so this is the function. So this is E of t, t, and this is 0.5 to 2, and this is minutes. And so it's half order. Ca naught is equal to 1 mole per liter, and K is equal to 2 moles to the 1/2, liters to the 1/2 minute. And it says determine X using the segregated flow model. And then, so I just want to, since we're using that model, I just want to write down the equations. So X is equal to 0 to infinity X of t E of t dt. So just going back to this reactor. So we have all these globules in here, and each one is in the reactor for a different amount of time. And so what we're doing is we want to assume that each one of these is an individual batch reactor. And so what you do is you solve the batch reactor equation, and that's what X of t is. So you'll get X of t from that. And then you multiply that by your time distribution function, so that takes into account how long each of these has been in the reactor. And then you want to integrate that from 0 to your time. So in this case, it would be from 0 to 2. And so basically you're adding up all of these individual reactors and getting a mean conversion. And so anyway, the first thing we want to do on this is a mole balance, assuming that this is a batch reactor. So, because remember, just look at it like this. We're looking at just that, and we're saying, okay, this is a batch reactor because there's nothing going in or out of it. And so the mole balance, we have Ca naught dx dt is equal to minus Ra. And this is assuming constant volume. And then we have the rate. So if you look at the example in the book, they solve this using a first order batch reactor. So this is basically the same method, only now we have a half order equation. So the rate is equal to kCa to the 1/2. Stoichiometry, assuming liquid, and so then we want to combine this. And what we want to do is combine the equation, integrate, and basically solve it, and then solve for x. So Ca naught dx dt is equal to k Ca naught to the 1/2, 1 minus x to the 1/2. So I'm going to erase some stuff real quick. So write down this equation just so you see where we're heading. So, all right, so I want to separate and integrate this, and so let's see, where am I at? I'm going to divide the Ca naught over. So if I do that, I get dx dt is equal to k Ca naught to the 1/2, 1 minus x to the 1/2, because when I divided this over, I have Ca naught to the 1/2 divided by Ca naught, so that's 1 over Ca naught to the 1/2. So then I want to separate and integrate, so I have 0 to x dx over 1 minus x to the 1/2 equals k Ca naught to the 1/2, 0 to t dt. And then I got this integration. I just got that. This one isn't in the table in the back. I just got it off a table, but not in your book. So, but you can do this on your calculator too, most likely. So anyway, you get 2 minus 2, 1 minus x to the 1/2 is equal to kt Ca naught to the 1/2. And so then I'm going to plug in 1 for Ca naught and solve for x. And if I do that, I get that x of t is equal to 2t minus t squared. So now I know what x of t is. I know E of t because it was given. So if I plug everything back into that equation, I have x is equal to, and then this is from 0 to 2. And I have 2t minus t squared. And then this is just equal to 0.5 from 0 to 2. So 0.5 dt. But this, depending on what you're given, this could also be a function. So just make sure you're putting in the correct thing for E of t. And so then if I solve this, I get that x is equal to 0.67. And then there's just some other things that you could potentially look at in Chapter 13. There's the mean residence time. And somebody erase this. So mean residence time, so Tm is equal to 0 to infinity t E of t dt is equal to tau. And this tau is equal to the space-time tau if v is equal to v naught. So there's also the variance about the mean residence time, and that is equal to 0 to infinity t minus tm squared e of t dt. And then there's also the cumulative distribution function. And this is all the material that's been in the reactor in like t or less time. So f of t is equal to 0 to t e of t dt. And you can see how that would make sense. Because this resonance distribution function, so just draw that again. So e of t and t. So let's say it looks like that, and say you sum from here to here, then when you take this integral, you'll get this. So you're basically adding up what's been in the reactor. And so that's basically it. So I don't necessarily consider this a cumulative review because there's not time to cover every single thing, but I touched on the things that I was specifically asked about, and I just tried to point out what I considered helpful in the book as far as the various tables and whatever else. So anyway, I hope this was helpful, and good luck.